Module 7D, we're going to focus on heat capacity. So we want to define heat capacity, specific heat capacity, and molar heat capacity. We're going to perform calculations involving heat capacity and specific heat capacity. We're going to start using our MCAT equation. This equation is very important. Memorize it. Just memorize it right now. You're going to see it again in second semester. You need to be able to calculate delta H for reaction from calorimetry data. Describe the function of constant pressure and constant volume calorimeters, and use them to calculate energy changes associated with temperature changes. So first, what is calorimetry? Calorimetry itself is defined as the measure of heat flow. It's a technique, it's a concept, it's how we measure heat flow. A calorimeter itself is the actual instrument that we use to measure the heat flow. So calorimetry is just like a broad measure heat flow. Calorimeter is the device used to measure that heat flow. We have two types of calorimeters, a bomb calorimeter, which I have a picture for in a later slide, and a coffee cup calorimeter. Coffee cup calorimeter, as shown here, this is what you guys will actually, well, not everyone. If you take general chemistry lab here at TCU in spring, you will use the coffee cup calorimeter. Most schools, you'll do this in a first semester lab. We just don't have first semester lab here. But it's just that it's coffee cups. So the difference, and we'll delve into this a little bit more, but a bomb calorimeter is a constant volume calorimeter where the change in energy is equal to Q sub V. Again, sub V meaning constant volume. And a coffee cup calorimeter is a constant pressure calorimeter. So because we're at constant pressure conditions, we have delta H. What is heat capacity though? Well, heat capacity is kind of like its name implies. It's the amount of heat, it's the capacity of something to absorb heat. So heat capacity itself is defined as the amount of heat required to raise the temperature of a substance by 1 degree Celsius. For example, the heat capacity of a 10-gallon fish tank versus a 10,000-gallon swimming pool. Obviously, they will have different heat capacities. It will take a lot less energy to heat a 10-gallon fish tank by 1 degree C than a 10,000-gallon swimming pool. The problem is that that's not very specific, because we could say, well, the heat capacity, this is that. Great, that's a relative concept though. If I have a 10,000-gallon swimming pool, it's going to take a lot of heat to raise that temperature, but that amount of heat is a lot compared to the fish tank. So instead, we talk about heat capacity in a general term, yes, but we often use specific heat capacity because it's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree C. It's just more specific, saying for 1 gram of substance, because now I can compare that swimming pool to the fish tank. They're relative to each other now. An important equation here is our MCAT equation. You do need to know this equation. I call it MCAT because of the MC delta T. So you'll hear me refer to it as your MCAT equation. You can use it whatever you'd like. Some people call it their Q equation. Some people call it their heat capacity equation. It's not quite heat capacity equation, although that's in it. I don't care what you call it, as long as you remember it. What do these terms mean? Q, heat. M is mass in grams. Most often, it doesn't have to be grams. It's going to be units that match to your C. C is specific heat. And watch the units, because they may change. You will often see units in joules per gram degree C. You may find them in kilojoules per mole K. Depends on the system you're using. Biggest thing is we need to make sure that the units here, the grams, match the units here. Grams, moles, whatever you're using. And the units on temperature match the units here. And that's why they can change. And then delta T is temperature final minus temperature initial. Your molar heat capacity is the heat capacity of 1 mole of material, hence the word molar. You may or may not have figured this out already, but the word molar means per 1 mole. So the molarity of something per 1 mole. it's actually per liter of solution there, but you've got how many moles you have per liter. Molar heat capacity per mole, the molar heat capacity of 1 mole. So this word molar means for 1 mole. Calorimeters. Again, I told you guys we have coffee cup and bomb calorimeters. So here's a slight difference between your calorimeters. Constant pressure calorimeters, delta H equals Q at constant pressure. So we can say delta H equals Q sub P. We have specific heat, joules per gram degree C, or molar heat capacity, joules per mole K. Just another number you guys will have to know, the specific heat of water is equal to 4.184 joules per gram degree C, and this is an exact measurement. So you do have to know this value. Memorize it. It's a good one to know. You're going to use it all the time. You'll probably memorize it just from doing practice problems. We can also have a constant volume calorimeter, where delta E equals Q at constant volume. Notice, though, we use delta E here. It's not delta H. It's not under constant pressure conditions. We're under constant volume conditions. We're measuring change in energy. We use a calorimeter constant for these, so kilojoules per degree C or kilojoules per K, because we're heating up a sample in a calorimeter, and we need to take into account the amount of energy that's going to heat up the calorimeter itself. That's called our calorimeter constant. So again, coffee cup calorimeter, you've got 2 nested styrofoam cups with some kind of lid on top, a stirrer mixing your solution and thermometer measuring the temperature, and you've got your solution in here where the reaction occurs. Usually your solution is your surroundings. We're monitoring the solution, knowing that the reaction is occurring within that solution. So the reaction is your system, the solution is usually your surroundings. In a bomb calorimeter, we put your sample in this cup and we burn it. It's called a bomb calorimeter because we're building up pressure, but we're not letting it expand. It's got a constant volume here. The Q of your system, the heat from the system, heat gained by the system is lost by the surroundings, or vice versa. Heat lost by the system is gained by the surroundings. So if your system gains heat, and Q is a positive value, then the surroundings had to lose that heat. And their Q is a negative value. If your system lost heat, their Q would be a negative value, and the surroundings would gain that heat that was lost. And their Q would be a positive value. So they're always opposite of one another. The heat lost by one is gained by the other. They're always, one's going to be positive, one's going to be negative. So your system versus your surroundings. Okay? We just have to define what's your system, what's your surroundings to be able to determine which is getting the positive values. Let's go ahead and work some examples so you can actually see this in play. How many joules of heat must be removed from 100 grams of mercury to cool it from 20 degrees C to its freezing point at negative 39 degrees C? The specific heat of mercury is 0.140 joules per gram degree C. I'm going to use my MCAT equation for this. How do I know I need MCAT? Well, I want to know joules of heat, so Q, removed from 100 gram sample, there's a mass, to bring it from 20 degrees C, T initial, to negative 39 degrees C, T final. And I'm given the specific heat, value C. I'm given everything I need for this equation. Q is what I'm trying to solve, and I'm told it's 100 grams of mercury times specific heat of mercury times my change in temperature, T final minus T initial. Negative 39 degrees C minus 20 degrees C. Now, these questions, I highly recommend you check your temperatures here. The change in temperature here is negative 59 degrees C, because notice this limits my sig figs to 2. If I calculate this out, I get negative 826 joules, which is the correct answer, but not the correct sig figs. So I need to round this to either negative 830 joules, or I could say negative 8.3 times 10 to the minus 2 joules. If you wanted this in kilojoules, you could say negative 0.83 kilojoules. All of those are correct answers. Given this table of specific heats, lead 0.128 joules per gram degree C, aluminum 0.902 joules per gram degree C, and water 4.18 joules per gram degree C. 100 grams of each, lead, aluminum, and water, are placed in the sun for 1 hour. Okay, so we've got let's say this is lead. This is aluminum. And so you can actually see it. I had the white on. Let's say this one is water. Okay, and let's pretend these boxes are actually the same size. I place all of these in the sun for 1 hour. They all absorb an equivalent amount of heat. So, amount of Q went in, amount of Q went in, amount of Q went in. Which one has the highest temperature at the end of this? Lead, it takes 0.128 joules of energy to heat up 1 gram of lead for 1 degree C. So 0.128 joules for every 1 gram, 1 degree C. By 1 degree C. For aluminum, 0.902 joules for every 1 gram will heat up 1 degree C. Water takes 4.18 joules for every 1 gram by 1 degree C. Hopefully you guys recognize that the one that will have the highest temperature would be lead. It takes 0.128 joules to raise 1 gram of lead by 1 degree C. I have 100 grams here. I have 100 grams of each sample. They've all absorbed the exact same amount of heat. The lead's going to heat up the fastest because it has the lowest heat capacity. It will have the highest temperature. It takes the least amount of energy to raise that sample. Water, on the other hand, will have the lowest temperature after 1 hour because it has the highest heat capacity. It can withstand absorbing that heat the fastest. The way that my brain saw this, now I see it by the definitions and by the values. When I was your age, the way I saw it, or educational level, age 2, the way I saw it was that I thought about like being in a car in summer. And now, if you're from the South, you really understand this. If you're from the North, you think you do. Trust me, you don't. Born and raised in Minnesota, and now I live in Texas, so I really understand what heat means in Texas. You get in your car in summer. I'll never forget. It was summer, and I had gone to this place called Valley Fair. It's like Six Flags, Minnesota. And I'd gone there with my best friend for the day. And I came out, and I found a water bottle in my car, and I was dying of thirst. And I had this water bottle that had been sitting in my car all day. But I was so thirsty, and I drank a little bit of it. And I was like, oh, this is so warm. This water is so warm. It was warm. It absorbed heat all day. But then I do things like, come to Texas and accidentally touch the metal part of the seatbelt in the dead of summer when your car has been parked in the sun. And you burn yourself because the metal is just so hot. See, that water was warm, yes, and it was unpleasant to drink, but it wasn't boiling hot. That metal, though, left a scar on my side where I accidentally touched it to my skin. Not a scar permanently, but it gave me a nice red spot because the metal was so hot, because metals absorb heat so well. And it's because metals have very low heat capacities. It's a good thing. They're great conductors of electricity. They're great conductors of heat. But they absorb heat very well. They have very low specific heats. Okay, another example. When 1.010 grams of sugar is burned in a bomb calorimeter, the temperature rises from 24.92 degrees C to 28.33 degrees C. If the calorimeter constant, that's what I was looking for, is 4.90 kilojoules per degree C, find your change in energy for burning 1 mole, and then it gives you the formula of sugar. So we're going to use your MCAT equation, but instead of using the mass in here, we use the calorimeter constant times your change in temperature. So it's slightly simplified. We don't have to put mass into here. We'll figure that out in a sec when we look at how many kilojoules per mole. But for the heat itself, we're just looking at how much heat was generated in that calorimeter. The calorimeter itself has a capacity of 4.90 kilojoules per degree C. The sample was heated up from 24.92 degrees C to 28.33 degrees C. 28.33 is our final temperature, and 24.92 is our initial temperature. This gave me 16.7 kilojoules. I still recommend checking this. This gives me 3.41 degrees C. So from 4 sig figs to 3, this has 3 sig figs as well, so we keep 3 sig figs. And then you note that the degrees C's have canceled out. So 16.7 kilojoules. But I want to know how much energy does it take to burn 1 mole. Well, how many moles do I have? Number of moles of C12H22O11, 1.010 grams. Convert that to moles. Its molar mass is 342.3. .00295 moles of sugar. So, I want to know how much to burn 1 mole? Well, let's figure out. That means number of kilojoules per mole. I burned 16.7 kilojoules, or I generated 16.7 kilojoules of energy as my change in energy, and that was based on 0.00295 moles, which means sugar would burn 5,661 kilojoules per mole. With sig figs, that is 5,660 kilojoules per mole. So, a lot of energy coming off of that. Sugar can give you lots of energy. The specific heat of copper is 0.387 joules per gram degree C. The molar heat of fusion of water is 6.0 kilojoules per mole, which is the energy needed to melt the ice at its melting point of 0 degrees C. Fusion means melt. You fuse things together. And what that's telling me is that it takes 6.0 kilojoules to melt 1 mole of ice. It's also a conversion factor. At 0 degrees C. If a copper rod with a mass of 225 grams is heated to 80 degrees C and then immersed in 100 grams of ice at 0 degrees C, how many grams of ice will melt? So some things to think about here. We're going to heat up, so we're going to take this copper rod, we're going to heat it up to 80 degrees C. We're then going to submerge it in a beaker of ice. That heat is going to transfer from the copper to the ice. We know that heat transfers, right? I mean, when you park your car at work in the summer, you come back hours later, the inside of your car is a lot warmer. That in winter, the opposite happens. The inside of your car gets a lot cooler. It's because of the transfer of heat. The system's going to equilibrate with whatever it's around. So when energy is transferred as heat, the direction of energy transfer is always from your hotter object to the colder object. It's never opposite of this. It never goes from the colder object to the hotter object. It always goes hotter to colder. So the heat is lost by the hotter object, gained by the colder object. With that in mind, I can comfortably say that heat will be lost by copper and gained by the ice. So negative Q of the copper will equal positive Q of the ice. Let's figure out what Q of the copper is. Q of copper, got 225 grams of copper. Remember, Q equals MC delta T. Specific heat of copper, 0.387 joules per gram degree C. And my temperature. I'm heating it up to negative 80 degrees, or up to 80 degrees C. But then I'm putting in ice, which is at 0 degrees C. So 0.0 degrees C minus 80 degrees C. This does have an extra sig fig on it, yes. This should be 80.0 degrees C. This is negative 80.0 degrees C, so I keep my 3 sig figs. This gives me 6966 joules. I'm going to underline the 6. I technically have 3 sig figs here, but I don't want to round you because I don't want to round off there. Or 6.966, underline that 6 kilojoules. So that means that 6.97 kilojoules of heat was lost by the copper, which means that the heat gained by ice is positive 6.966 kilojoules. Now I know it tells me that it takes 6 kilojoules of heat to measure 1 mole of 1 mole of ice at 0 degrees C. So how many grams of ice can I actually melt with 6.96 kilojoules? Number of grams of ice melted, 6.966, still underlining that 6 kilojoules. This here is a conversion factor. This tells me 1 mole of ice to 6.0 kilojoules of ice. That cancels out my kilojoules. Now I've got moles of ice. I know there's 18.02 grams of ice per mole. (21 grams of ice melted. So, am I able to melt all my ice? Nope. I'm able to melt about 20% of my ice. How do I know that my final temperature is 0? Well, truthfully, that comes from just some intuition and some calculation. So the fact that all of this heat would only melt 21 grams of ice means that, yeah, it will actually go down to 0 degrees C as my final temperature. Now, if I had more energy than ice there, then you could probably argue that, would your final temperature really be 0? Yeah, we're still going to assume your final temperature is 0. We're still going to assume it goes all the way down to there. But we know that not all of your ice is actually going to melt. Let's work one more example for this unit. Bomb calorimeter example. We have a 4.25 gram sample of cyclohexane, C6H12, being combusted. Again, combustion means burning. So C6H12 plus O2, giving you CO2 plus water. In a bomb calorimeter with a total heat capacity of 5.86 kilojoules per degree C, this is your calorimeter constant. The temperature of the calorimeter was increased from 23.5 degrees C to 39.8 degrees C. What is the heat of combustion for cyclohexane in kilojoules per mole? So we put your sample in here, we burn it in the presence of oxygen, and we monitor the temperature increase. Our Q is equal to our calorimeter constant, 5.86 kilojoules per degree C, times our temperature difference, 39.8 degrees C minus 23.5 degrees C. If you check this, the temperature difference here is 16.3 degrees C, so we keep our 3 sig figs. This gives me 95.5 kilojoules. I want this in units of kilojoules per mole though. So how many moles of cyclohexane do I have? I start with a 4.25 gram sample of cyclohexane. Convert that to moles. Molar mass of cyclohexane is 84.16. This gives me 0.0505 moles of cyclohexane. So for my kilojoules per mole, 95.5 kilojoules was burned for 0.0505 moles of sample, which means that for cyclohexane, it's 1,890 kilojoules per mole. It's kind of a lot of energy. That's why it's combusting hydrocarbons is advantageous to us. That is the end of Module 7D.